All right, here we go, video 2.4. So honestly, there's nothing really new here, but just from experience, one of the things I've tended to see students struggle with is graphs. And so this video is just going to be about some of those main concepts that you need to understand about the graphs, because they are definitely a recurring thing throughout this course. All right. So at this point, we're dealing with three different types of graphs. All right. We've got position time graphs. And so basically you should know that if you find the slope of a position time graph between two different points or two different times, that gives you the average velocity between those 2 points. Whereas if you find an instantaneous slope, or the slope of a tangent line, that gives you the instantaneous velocity. Okay? So, in simple words, slope of a position time graph gives you velocity. Cool? Similarly, for a velocity time graph, the slope of a velocity time graph gives you acceleration or average acceleration, right? If you find the straight line slope between 2 points, it gives you the average acceleration. If you find the instantaneous slope, the slope of the tangent line, that gives you the instantaneous acceleration. All right. New this year, that we did not talk about a ton in honors, is that when you find the area under a velocity time graph, it gives you displacement, right? So that would be like taking a definite integral, right? So if you've got time and velocity, if your velocity is, whatever, 6 meters a second, and you want to find out how far you went in 5 seconds, then that's 6 meters a second times 5 seconds is 30 meters. That's the same as the area under the graph, right? Okay, so the area under a velocity time graph gives change in position, and then similarly, the area under an acceleration time graph gives us change in velocity by kind of the same logic, right? Okay, so let's see if we can apply that to some examples here, all right? So let's dual page this here. Okay, so, get rid of the clock. Okay, so, all right, so here on the left, we've got this position time graph, and over on the right, we've got these questions. Question number 1 says, to describe in as much detail as possible the motion of the object. Use numbers where possible. All right, so take a second, pause the video, see if you can answer that, and just while you're at it, try to answer the other ones too, right? Okay, so I'm going to assume you did that. All right, and then let's talk about what's going on. So the idea is our object is starting with at a position of negative 12. So we've got some number line. Our object is starting at a position of negative 12. Because my position is increasing, that tells us that we're moving in some sort of positive direction. It looks like for the first 7 seconds, it looks like, the velocity is constant. Specifically, it looks like every second we're going 1, 2, 3 meters, right? So this is velocity equals 3 meters a second, right? And then it looks like once you get to here, it looks like we start slowing down, right? Because the graph gets less steep, less steep. Up here, at this point, your velocity is 0. That's where you stop moving forward and begin moving backwards. So then the velocity gets more and more negative until it looks like around 15, it might be 14 seconds, but somewhere in here, the velocity becomes constant again. Okay, and so if you count from here, it looks like every second the position decreases by 1, 2, 3, 4, 5, it looks like. So now my velocity is negative 5 meters a second, okay? Now, during this chunk here where the velocity is changing, we might be able to find the acceleration if we knew that that was a parabola, and we could definitely analyze it. I guess the one thing we can certainly say is that the acceleration is negative, right? Because our velocity is going from positive to negative, right? And we could probably use some kinematics equations and find that acceleration if we wanted to. But to do that, we would have to know that the acceleration here is constant, okay? And we don't, just by looking at the graph, we don't necessarily know if that acceleration is constant, okay? It does turn out that it is. Okay, so that's number 1. Number 2 wants the average velocity for the 20 seconds shown. All right, well, remember, average velocity is displacement over time. So, for the 20 seconds shown, average velocity is displacement over time. Okay? So for the 20 seconds shown, the position goes from a position of negative 12 to a final position of negative 24. So negative 24 meters minus negative 12 meters over 20 seconds, right? So it looks like my displacement is negative 12 meters, right? Divided by 20 seconds. So it looks like that's negative, what, 2.4? No. What is called divided by 20? That is the same as 6 divided by 10, so 0.6 meters per second, all right? So what that represents is the slope of this straight line, right? Because we just did rise, which is negative 12, over run, which is 20. Okay? Number 3 wants the average speed. Well, I guess technically then what I should have done is I should have put a little arrow over these, right? Because those are all vectors. Okay? So average speed, remember, is just distance divided by time. So here I actually need to figure out what distance my object traveled and divide it by the time. The distance isn't negative 12 meters, right? So what I need to do is I need to figure out how far did my object move forward and how far did it move backwards, right? So let's see, here we're at a position of negative 12. This is the point where we stop moving, and it looks like there the position is, and you guys might not be able to see this on your printout, but it looks like it's halfway between 12 and 15. So that's 13.5 meters. Okay? So that means that between here and here, we went from negative 12 to 13.5. That's 25.5 meters, right? Okay? And then from there, we went all the way back to negative 24. So we went that same distance plus another 12, so that's 37.5 meters. Remember your distance, you don't need to worry about direction. So, all right, so the distance that I traveled looks like it's 25.5 meters forward, plus 37.5 meters backwards, and that took 20 seconds. So what is that? So 26 and 37 is what, 63 meters, I think, over 20 seconds. And so that's 3.15 meters a second. Okay. All right. So let's see. Number 4 wants the velocity at t equals 2 seconds. Well, so what I want is the instantaneous slope, right? Because that's asking for an instantaneous velocity, so I want instantaneous slope. So I want the instantaneous slope right here at 2 seconds, right? Oh, but this is a straight line, so I really just want the slope of this line, right? And just by counting, we can see that every 1 second, our position increases by 3. So that was just 3 meters a second. Okay, let's see. After 10 seconds, that's right here. Oh, that's where you stop, right? Because your tangential, the slope of your tangent line there would be 0, right? So number 5 is 0 meters a second. Now, what about after 11 seconds? So doing that would require some more math, all right? I wouldn't really ask you to do something like this. It seems a little bit algebra-y, but if I told you that the acceleration here was constant, you could use kinematics equations and find the acceleration there. I think the acceleration, if I remember right, well, let's do it. Whatever, we have time, right? Or at least I got time, I don't know. So let's see, what do we know? We know that right here, we know that our velocity is 3 meters a second, right? Oh, this is super easy, right? And we know, let's see, we know that right here, our velocity is negative 5 meters a second, right? And how much time did it take for the velocity to change? Well, that's between 7 seconds and 15 seconds, that's 8 seconds. So my acceleration is Vf minus Vi over t. So at the end of that acceleration period, my velocity is 5 meters a second. Negative. At the start of it, it's 3 meters a second. Time is 8 seconds. So the acceleration is negative 1 meter per second squared. So after 11 seconds, let's see, we're going from here to here. So we're going from 7 to 11, so that's 4 seconds. So Vf equals Vi plus At. So my starting velocity here is 3 meters a second. My acceleration is negative 1 meters a second squared. And I want the velocity 4 seconds after we're at 7, right? So that's negative 1 meter per second. Cool? Or what I'm asking, what are you going to do? You're going to go, no. So if you have questions, put them in the comments or write them down and ask in class. All right, number 7, velocity after 15 seconds. We already established that was negative 5 meters a second. What's the speed at 16 seconds? Well, the speed is the same as the velocity, but without the negative, and so that's 5 meters a second. So this one is negative 5 meters a second. This one is 5 meters a second. All right, so that's the deal. That's stuff you should be able to do with position time graphs. All right, let's take a look at a velocity time graph. Okay, so here we got this velocity time graph. All right, so number 1, once again, asks you to describe the motion. So see what you can figure out here. So all of these problems, 1 through 7. I'll pause the video, or you pause the video. All right, I'm going to assume you have paused the video. So what's going on here? Well, during this chunk, our velocity's, what, negative 8, it looks like. And then after 5 seconds, the velocity begins to increase. It looks like every second, the velocity increases by 2. So my acceleration here is 2 meters per second squared until you get to, it looks like 12 seconds, right? And then your acceleration increases. Okay? So that is that. I guess we should establish one other thing. At this point right here, the velocity is 0. So everywhere on this side, we're moving in a negative direction, and everywhere over here, we're moving in a positive direction. Okay? So it looks like you're moving backwards quickly, then you go backwards slower, 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 stop moving backwards, and then start moving forwards faster, 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 and then you increase how quickly you go faster. All right? So that's number 1. Number 2, the acceleration at 3 seconds. What do you got? Velocity's constant, right? So for number 2, our acceleration is 0. Number 3 wants the acceleration after 8 seconds. We already did that. That's 2 meters a second squared. Number 4, the acceleration at 15 seconds. So this is a thing that I don't know that you would ever be asked to do this, all right? I don't think I've seen this a ton. But so what you would be doing there, and I guess you could approximate it if you wanted to. So you could grab a straight edge and find the tangent line, draw on your tangent line, which would look something like that, right? And then find the slope of that. But that's about the best you can do with that. So based on this graph, there's not a ton you could do there. All right. You could, I suppose, calculate the jerk, which is how quickly the acceleration changes. It's the derivative of acceleration. But that never comes up on the AP test, weirdly. So I think we're done with 4. I think that's all we can do. All right, number 5 wants the average velocity for the first 5 seconds. Average velocity for the first 5 seconds. Average velocity for the first 5 seconds. Oh, well, the velocity there's negative 8 the whole time. So since the velocity is constant, our velocity is negative 8 meters a second. Average, right? Because you're always going at that speed. Now, what about the average velocity for the first 10 seconds? Ooh. This is where students mess up. All right, so let's do this. So number 6, we want the average velocity for the first 10 seconds. So I ought to be able to do this, right? No, you cannot use that because here my acceleration is 0 and here my acceleration is 2. my acceleration is not constant, so you cannot do this, right? The only way you can calculate average velocity when your acceleration is not constant is to use the definition, displacement over time. So how do I find the displacement? Well, remember, displacement is a definite integral of velocity with respect to time, and I want for the first 10 seconds. So this is the area under the curve. Remember, integral represents area. So what I want is the area under the curve for the first 10 seconds. So here's my x-axis. Here's 10 seconds. So what I need to do is I need to find this area, which is a negative, and then this teeny little positive bit, right? So do a little math to find that area. All right, so let's break it up into chunks. So this chunk here has an area of -8 times 5, so that's -40. This chunk here, let's see, my altitude here is -8, this side is 4, so 1/2 base times height, so that's going to be -16. And then it's also this tiny little sliver over here where it's positive, so that's going to be 1/2 of 1 times 2, right? That's 1 second. This is 2 meters a second. So it looks like my displacement is -40 minus 16 plus 1. So -56 plus 1 is -55 meters in 10 seconds. So -55 meters per second is my, 5.5, sorry, meters per second is my average velocity. Okay? And then to do number 7, it says what's the average velocity for the first 15 seconds? Well, you just got to keep going, right? So you have to then find, it looks like to here, we can find this area, right? So that area is going to be, what, 3 times 6, and then half of that, so that's 9. And then here, this last chunk, this side of the thing is not straight, okay? And I've seen AP problems where you have to approximate. So it basically is just counting boxes, okay? And just know that you're approximating, right? So let's see, I'm counting 3, 4, 5, 6. Those are the whole ones. This little chunk here and this little chunk look like they make another 1. It looks to me like this chunk and this chunk make another 1, so I'm going to keep tabs of my others. 1, 1. And then maybe this chunk and this chunk makes another 1. And maybe this and this makes another 1. And I don't know, maybe a half there, okay? So whatever, add them up and then divide by 15, okay? Oops, I went past 15, I went all the way to 16. But whatever, you get the idea. It's going to be an approximation. And that's the best you can do for 7, is just to approximate the area, all right? Without knowing the equation, right? Because we can't really take an integral without knowing the equation, okay? So finally, let's look at an acceleration time graph, all right? So same drill, pause it, answer them, see what you can do. All right, so we can't say a ton about the motion of this thing because at no point do we know the direction that the object is traveling, right? Knowing that the acceleration begins at 12 tells us that the velocity is increasing, but I don't know if it's getting more positive or less negative, right? So we can't say a whole lot here about the motion. All I can say is that the velocity is increasing, and then the velocity keeps increasing, but at a slower rate. Now my acceleration is constant for a fraction of a second, instantaneously constant, and then the velocity decreases and then keeps decreasing, right? Okay, so we can't really say a lot for for number 1. Number 2 wants the acceleration at 3 seconds. Well, read the graph. 1, 2, 3, acceleration is 12. Number 3, acceleration after 8 seconds. 4, 5, 6, 7, 8. So it looks like it's -3. Number 4, acceleration after 15 seconds is, what is that, -6. 5 wants the average acceleration for the first 3 seconds. Well, for the first 3 seconds, it's constant, right? So it's still 12 meters a second squared. Okay. Number 6, average acceleration for the first 10 seconds. Well, number 6, average acceleration is, by definition, change in velocity over time. How do I find the change in velocity? Oh, remember, change in velocity is the integral of acceleration with respect to time, but since I'm looking for a change, it's a definite, right? So for first 10 seconds, so 0 to 10. So once again, you're going to find the area for the first 10 seconds. So I need to find these areas, right? So this guy here is 12 by 3, so that's 36. This guy here is 12 by 1, 2, 3, 4. So 12 times 4 is 48, but then half of that because it's a triangle, so 24. And then down here we've got some negatives. 2 by, what is this, -6? So 2 times -6 is -12, but we want half of it, so -6. And then we've got this other little chunk here, which is 1 by -6, so also -6. So my change in velocity is 36 plus 24 minus 6 minus 6. So that's the same as 36 plus 12, so 48 meters a second in 10 seconds gives you 4.8 meters per second squared for an average velocity. All right. All right. Finally, question number 7. I like this one. Question number 7 says, assuming the acceleration remains constant at -6, right? Because here it's -6. Assuming the acceleration remains constant at -6 after the graph stops showing data, when will the object return to its original velocity? We don't know the initial velocity. Okay, but what we want to do is we want to find the point at which our change in velocity is 0. Oh, that means when is the area 0? All right, well look, here's what we know. We know that this has an area of 60, right? So when does the area over here equal -60? Well, let's see. So after 10 seconds, we've subtracted 6 twice, right? So now we're down. So how many more do we need? Well, we need another 8 times -6, right? So another 8 seconds from this line, right? Because we need 10 -6s, right, to get to -60. We've already got 2 -6s, and I need 8 more. So 1, 2, 3, 4, 5, etc. So I can't read my graph. So that's 10, so it looks like we're at 18 seconds. All right, there you go. Graphs. I think that's it. That's it. Bam. How did we do? 23 minutes. Not too shabby.